Hi everyone. First of all, I have to apologize for Monday that my absence. My apartment got an internet problem for our floors, and I can't make it. So as I promised before, uh, from this assignment, I will be recording everything and sending the YouTube links so that you can watch them after our regular learning team time. Because I noticed that sometimes some of you have some internet problem and have to like leave during the session, and yeah, so I guess it would be a good idea to have these things recorded, and so that so that you guys can watch them whenever you want. Okay, so let's start. So today we are going to talk about two-charge electric field. Let's read the problem statement together. Two charges are placed on a line as shown. For each case, determine whether or not electric field is zero somewhere to the left, in between, or to the right of the charges. So in the first problem, we can see that Q1 and Q2, they are both positive. And recall what we discussed before. If we have a positive charge, then the electric field is something like this, right? It's going from the charge to the outside. So in this region A, the first electric field is generated by charge A. We label it as E1, and it is in this direction. And because this is also a positive charge, then E2 will also be in this direction. Therefore, if we add this vector and this vector, because they are in the same direction, so that they cannot be zero. And here, in the middle region, E1 points to the right, because the positive electric charge Q1 is on the left, and E2 is generated by the second charge, so it's pointing to the left. It's pointing to the left. So the question is there a position in the middle that these two vectors have the same magnitude but opposite direction? So let's recall the formula for electric field. E equals to K times Q1 over R squared. K times Q over R squared. So let's take it as an example. We have this line and point Q1 and Q2. So if I choose a position here, and this is R1, and this will be R2. Alright? So the electric field at this position is E1 equals to K times Q1 over R1 squared. And E2 and E1 is pointing in this direction. and E2 equals to K times Q2 over R2 squared. It's in this direction. And we can see that Q2 is larger than Q1, alright? Q2 is 20, Q1 is 10. Which means that this number, Q2, is larger than this one. So if we want these two quantities to be equal, then this means that R2 has to be larger than R1. Because Q2 is larger than Q1, then if we want E2 to equal to E1, then R2 has to be larger than E1, which means it's somewhere over here where we have this R2 larger than R1. Then we could have a situation where K times Q1 over R1 squared equals K times Q2 over R2 squared. Right? Okay. So yes, there exists a position in region B that electric field is 0. So in region C, because E1 and E2, they both pointing to the right, because both of the positive charge are locating at the left-hand side of this region C. So there's nowhere in region C that could have a 0 electric field. Okay. So now let's move to part B. So now we have a positive charge and a negative charge. So now what's different is that E1 here is still the same. It's still the same. It's pointing to the left. However, E2, because it's a negative charge here, and E2 will be pointing to the right. Will be pointing to the right. Will be pointing to the right. Because the electric field of a negative point charge is pointing like this. Okay. So now let's ask ourselves, can we have this relationship again? This relationship. So now we can see that Q1 is smaller than Q2, right? Q1, Q2. And our R1 is this. And R2 is this. Which means that we have a smaller Q1. Q1 is smaller than Q2. And also R1 is smaller than R2. Okay. And so the conclusion is that yes, we can have a position that these two quantities are equal. If you try to imagine this, that R2 is equal to R1 plus the distance in between, and this equation changed to K times Q1 over R1 squared equals to K times Q2 over R1 plus D squared. Okay, and Q1 is 10, Q1 is 10, Q2 is 20, and K, we cancel out K, and what? Okay, and then we have R1 plus D square over R1 square equals to 20 over 10, which is 2. Okay, and we take a square root of both sides, which means R1 plus D over R1 is root 2. Okay, so yeah, you get it. There is a solution that we can cancel this 2 electric field out. Okay, then in the middle part, E1, because the positive charge is on the left, so E1 is pointing to the right, and E2, because although Q2 is on the right hand side, but it's a negative charge, so E2 also points to the right. Therefore, these 2 electric fields, they are in the same direction, then we cannot cancel them out. So there's nowhere in region B we can have a 0 net electric field. Okay. Then in this region C, E1 points to the right, and E2 points to the left. Pointing to the left. Okay, and now we have a different situation. It's still this equation. Let me rewrite this. It's still K times Q1 over R1 square equals K times Q2 over R2 square. But now R1 is smaller than R2. So now this is R1 and this is R1. Oh wait, sorry. This is R1. And this is R2. So Q1 is still smaller than Q2 because it's 10 and 20. Q1 is still smaller than Q2. And R1 is larger than R2. Which means that this thing is bigger and the denominator is smaller, which makes this entire number to be guaranteed larger than the left hand side, which means left hand side is guaranteed smaller than the right hand side because the numerator is greater and the denominator is smaller. Okay, which means we will not have this equal sign in the middle. We can only have this. The right hand side is larger than the left hand side. Therefore, there's nowhere in the region C that we can cancel this E1 and E2 out. The electric field will not be cancelled out. Okay, so this is the first worksheet on Monday.